Welcome to Chapter 13, Section 1, Representing Sample Spaces. This is for Integrated Math 2 or IM 2. So I'm going to be reusing some of these videos from a previous video, so the problem numbers may not quite match up, although you will see a title at the bottom to let you know which number it's supposed to be. It's just kind of a time saver there. Alright, so just to get started here on the front screen, the first thing you should see is your due date. I don't see that on my teacher preview, but you will see it on your student screen. The second thing is the number of attempts. We always have unlimited attempts on homework, tests, and quizzes. Number of questions just tells you how many are on this particular assignment. Grading policy is always best score, so whichever attempt is the best one is one you get to keep. And partial credit is enabled, so if you answer one of two questions correctly, you get credit for the one question, or however many you answered correctly. This also, if I understand correctly, goes into parts of a question too, if there's more than one answer within the question. There's partial on there too. Down here it says, please remember once you start your homework, you must finish it before you can work on anything else. And what that means is once I click start, down here in the bottom right corner, there's going to be a submit assignment button. This is how we finish an assignment. So what that means on the last screen is you can't work on anything because Alex is going to lock all of your other assignments and even the resources until you click the submit assignment button. What it's trying to do is leave this attempt open for you and not close it. If you say close this screen and you're not done yet, or you close your computer, it's trying to leave the attempt open for you. So just make sure that when you want to leave this screen, whether or not you finished, you click submit assignment so that Alex doesn't lock out all of your other assignments and resources. That's one huge reason to click that button. Another big one is that it actually affects the gradebook when you click that button, so that your teacher can see what you've been working on, and hopefully it will improve your grade there. All right, on the side we always have three resources. We have explanation. Explanation tells us that we're going to lose our current question attempt because it's going to give us the answer to this exact problem. So it's not going to give you the answers unless you come type them in. Example will give you something very similar to what it is we're looking at and kind of walk you through the idea here. Make sure you read through background information, especially if you see this section. If you don't see the background information, it's kind of introducing something brand new. That's the idea. So you can scroll through. Once you're happy with that example, you can close it. You can open another example so that you can see another one worked through if you need to. You can also message your teacher directly from the screen so we know where to come help you, because it attaches a picture of this problem on the email. So it's a good way to get specific help on a problem. All right, let's go ahead and get started. All right, so we are definitely getting started here in probability. And the first thing they have us do is looking at a tree diagram. And what a tree diagram does is it shows us how quickly options can kind of grow. That's kind of an easy way to put that. So in this one, it says Justin must choose a crust and a topping for his pizza. So there are three types of crust. We have regular, pan, or thin. And there are three types of toppings to choose from: pepperoni, sausage, or mushroom. And if you notice, for each choice for the crust, he has to make that choice for the mushrooms. So each pathway he takes splits again. And if we had even more choices, the more choices you have, the more splits, the larger this tree diagram can become. So they can definitely kind of get out of hand depending on the number of choices we have. They can get very large. So with this one, we can say, okay, I'm going to choose regular and pepperoni. So my path would be regular pepperoni, or I could choose regular and sausage. That's a different path. Or regular mushroom. Well, what if I wanted a pan pizza? Then I would have to decide, is it pepperoni with pan pizza? Is it a pan sausage? Is it a pan mushroom? Same thing with thin. So I have three options there. It's either going to be thin with pepperoni, thin with sausage, or thin with mushrooms. So it kind of just depends on the options I choose. So how many total outcomes are there? Well, we just look over here and say, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 different outcomes, 9 different possibilities or choices that I could make or Justin can make. We'll say Justin since it's him in the problem here. So how many outcomes have both thin crust and pepperoni being chosen. Well, thin crust would have to be down here. It'd have to be one of these ones. And if we want thin crust and pepperoni, there's only one possible pathway that chooses both. So we would only have one outcome that actually has thin crust and pepperoni. How many outcomes have regular crust or pan crust being chosen? So we have 1, 2, 3 regular or 1, 2, 3 pan. So that's 6 different outcomes for regular crust or pan crust. So we're just really counting this. We're just looking at it and showing these are the possible outcomes, possible choices for the situation, and then saying, okay, well, what does it mean? Can I interpret it? All right, so we're going to keep moving here. So now we're going to look at the introduction to the counting principle, because drawing the tree diagram, like I said, it can kind of get out of hand very quickly. Because with this one, let's say I wanted to draw a tree diagram, and it says Tony must choose a shirt, a pair of pants, and a cap for today's outfit. He has 3 shirts, 2 pairs of pants, and 2 caps to choose from. How many different outfits can he make? Well, so shirts, let's say he has a blue shirt, a green shirt, and we'll go with a red shirt. So here is his t-shirts. So these are his shirts. And he has to choose blue, green, or red. All right, well, what if he chooses blue? And let's just go with, he's got kind of 2 different kinds of jeans we're going to go with. So he's got jeans, I don't know what I did. So jeans, jeans 1 and jeans 2, like that. For each one, he would have to make that choice. So he's either going to wear jeans number 1 or jeans number 2. All right, so now he's made the choice. I'm going to go with blue shirt and jeans 1. Well, now I have to choose a baseball cap. So let's go with, I'm going to go with yellow. Why not? So he's 2 different baseball caps. So I'm going to say cap 1 and cap, and cap 2. If he did a blue shirt with jeans, the second pair of jeans, then he'd also have to decide which cap he was wearing. So you see how it's starting to get to that point where it's going to get a little tedious to draw this out, right? Because each choice I have to add on to the previous choice. All the choices, not just one of them, but all of them. So we definitely kind of have a bunch here, right? This one's not too bad. Because what if he had, how many of us only have 3 shirts, or only 2 pairs of pants, or only 2 baseball caps? I know I have a whole closet full of pants. So if I were to do mine, I'd probably have a whole lot more choices to choose from. I definitely have a couple of my favorites, but it just depends on how many. So this could get out of hand very quickly. Instead of having to draw this diagram each and every time, we can use what's called the counting principle. And just say how many options are in the first group? 3. There's 3 different pairs of pants or shirts. How many options are in the second one? Not all of these, just how many things do I have to choose from? I can either choose jeans 1 or 2. There's only 2 options there. Same thing with the caps. There's only 2 options. It's either going to be cap 1 or cap 2. So I can multiply these together and get the number of outcomes. So 3 times 2 is 6, times 2 is 12. And if I count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Look at that, it works out. So it just makes it very fast to know the total number of outcomes if you multiply using the counting principle instead. So I know I kind of went the long way around there to explain that, but I wanted to make sure that you understood where I was getting those numbers. All right, so we're going to kind of keep using the counting principle here. So LaToya is studying the growth of a particular type of plant. She's testing the effects of 3 growth factors: lighting, age, and temperature. Here are the levels she's testing for each. So we have lighting. There's low, medium, high, and very high. So that's 4. 1, 2, 3, 4. So she can put the plant in any one of those 4. Age, we have 1 month, 2 months, 3 months, 4 months. That's another 4. And temperature, we have 20 degrees, 22 degrees, 24 degrees, or 26 degrees, and these are all Celsius, not Fahrenheit. So that's another 4 options. So each one of these would have 4 options. So if we were actually draw a counting principle out, or not a counting, but a tree, I'd have to start off with 4 options instead of 3. Each one of those options would have a month on it, 1 through 4. So I can even, oops, clicked on the wrong thing here. Nope, don't save. So I'd have low, medium, high, very high, like that. And now I'd have 1, 2, 3, 4 for the lighting. 1, 2, 3, 4 for the lighting. 1, 2, 3, 4. And 1, 2, 3, 4. I don't know what I was drawing there. 1, 2, 3, 4. Like that. Now for each one of the months, and I'm not going to be able to draw this because I didn't actually give myself enough room, I'd have 1, 2, 3, 4 for the temperature. So we can see, hopefully we can see right away, this is going to get very busy, very, very quickly. It's going to be kind of hard to keep track of all of these if I were to do 1, 2, 3, 4 on each one of these, right? So instead, let's use the counting principle and say how many options are there for lighting? 4. How many options are there for age? 4. How many options are there for temperature? 4. We're going to multiply all these together. 4 times 4 times 4 is 64. So there are 64 possible ways or possible paths that she could choose for these plants. All right, let's see. We have determine a sample space and outcomes for a simple event for the next one. So we're going to delete that guy just so I can have a free space here. So a bag has 9 balls labeled A, B, C, D, E, F, G, H, and I. One ball will be randomly picked and its letter will be recorded as the outcome. Give the sample space describing all possible outcomes. Then give all the outcomes for the event of choosing a vowel. If there is more than one element in the set, separate them with commas. So this was just asking us to think about if we had the bag, and I reach my hand into the bag and I'm going to grab one of these, what possible things could come, which one could I grab? Could I grab the ball that has an A on it, or a B, or a C, or a D, or an I, or an H? I could grab any one of them. There's no way of knowing unless I actually looked before I went reached into the bag. But I'm not supposed to look. It's supposed to be kind of random here. I'm randomly picking one. So the sample space is all of them. Open. I'm going to do capitals. A, B, C, D, E, F, G, H, I. So all of them are in my sample space. But the event of choosing a vowel, that's a little bit more limited. Because now I'm only going to choose the vowels. So it would only be A, E, and I. Those are my only 3 vowels there. So it just wants us to list what are the possible options there to get what I want if I'm trying to choose an outcome. All right, and I think we're going to actually do a calculation for the next guy. So it says a box has 4 cards numbered 1, 2, 3, 4. Lucy will toss a coin once and record that toss as heads or tails. Then she will randomly pick a card from the box and record the number chosen. Give the sample space describing all possible outcomes. Then give all the outcomes for the event that the coin toss is tails. Okay, so this one I am going to do a little tree diagram just because it's a little easier to look at this. So first Lucy is going to flip a coin. So I don't know why that came out funny. So we have heads or tails for that coin. It's going to be one or the other. Those are my only 2 options. And then she's going to choose, randomly choose a card and record the number. So 1, 2, 3, 4. She could choose card 1, 2, 3, or 4. Same thing for tails. It's not going to change her procedure if she lands on tails or heads. So with this one, the way we would write these outcomes is we write it as H1, H2, H3, H4. So I landed on heads and I picked a 1. I landed on heads and I picked a 2. So this one, it's the same thing. It'd be tails 1, tails 2, tails 3, or tails 4. These are all my possible outcomes. That's the way they want us to write it. And they even show us that here. Use the format H1. So these are my sample spaces. So I have H1, H2, H3, H4. And they're not going to be picky if you don't have these in order like this. I'm just writing them in order because why not? But I don't think they're going to care if you did H1 and T1 and then H2 and T2. They're not going to necessarily care on that one. So those are all of our possible outcomes. And then we want to do the event for then give all the outcomes for the event that the coin toss is tails. All right, well, that means that we want it to be tails. We want it to be one of these 4. So these are the 4 that we're looking for, and I'm going to be a little bit lazy and just copy and paste them down here so I don't have to retype all those. Check. All right, so that was section 1. I will see you in section 2.